Extremely good.
Yeah.
Okay, perfect.
It's going online now. Good. Just then we have a delay of about a few minutes. A few minutes or two. Okay. Waiting for the thing to show up.
Extremely good.
Okay, sorry.
Okay, perfect.
Okay, sorry. You heard yourself, but it's just because it's the live streaming on the YouTube channel part. So let me go ahead and start as people are trickling in as usual. So it is a pleasure today to welcome you back to the online SPICE-SPIN+X seminars that are organized by the Spin Phenomena Planning Center here in Mainz, together that they do with Karen University, who is now in Duisburg, a professor in Duisburg, and SPIN+X Collaborative Research Center, led in Kaiserslautern and Mainz, led in Kaiserslautern by Martina Schliemann and Burkhard Hillebrands, and in Mainz by Matthias Chloe. We will have now in the fall, begin again, the regular seminars. Next week, we don't have one because there is the conference on transient magnetism that we have a link in there to check it out. If you show wishes online, so you could be able to see most of the talks. Once again, this is a webinar format, so please write your questions on the Q&A or afterwards raise your hands and I will give the floor to you can answer ask the speaker directly. It is my pleasure today to welcome a young talent in our field. Has been around in the field for a while now, but now she's a professor in Boston College. Benedetta Flebus, she's very international, mostly in Europe. She went from Italy, of course, where she's from, then to Paris, then to Switzerland, then to the Netherlands. So it's kind of almost going all the way through Europe, but then decided to jump ship and go to the US, where she has been a postdoc with Jaroslav Zakovniak, and I think Benedetta also with Alan as well. You were
Yeah, with Alan McDonald.
Now McDonald, and has started in Boston a year or two ago. She works on many aspects of spintronics, but in particular now she has been really driving a lot of the ideas on how to use light and periodic driving systems in these magnetic systems, which is very exciting, far from equilibrium type of or out of equilibrium type of physics. So with this, I'll stop sharing and ask you to go ahead, Benedetta, to share your screen and begin when you wish.
Thanks, Jairo. Thanks for the introduction and thank you for inviting me. So today I want to discuss 3 works. This work that was published last year and 2 works that are in preparation and actually hopefully soon they're going to be on the archive. And all these works have something in common, at least from my perspective. They are about try to unveil new phenomena in magnetic system by understanding the interplay between topology and dissipation. So generally, magnetic systems have been already extensively explored as potential platforms for creating analogs of the topologically non-trivial band structures that we all know in electronic systems. So there have been many works that have addressed this issue. Here I'm citing just some of them for the sake of space. And in general, the collective excitations of magnetic system, magnons, have been found to display topologically non-trivial band structure in the presence of a certain symmetry-breaking spin-spin interaction, such as, for example, inhomogeneity in the dipolar interaction, the Alodziński-Mourier interaction, or Kitaev interactions. So these models have succeeded in unveiling this type of phases in magnetic systems, but I will argue here that all these models rely on Hermitian models. And we can write down an Hermitian Hamiltonian only when our system of particles or quasi-particles can be treated as closed. So only when we can assume that the energy is conserved and therefore also the number of quasi-particles is conserved. But we all know, and experimentalists know this even better than theorists, that actually magnon spin-non conserving interaction, first of all with the crystalline lattice, but also with the electrons or impurities are definitely ubiquitous, and there is no way to get rid of them. We can find certain materials like yttrium, iron, garnet who have very low dissipation, but this does not matter, that the dissipation is not there and is not measurable. So how do we describe this dissipation? This is a very challenging task. So let me first focus on the simplest picture of magnetic dissipation. So let me take a ferromagnetic macrospin and try to describe its dynamics in the long wavelength limit. We all know, I imagine most of us in the spintronics seminar know how to do that. We can simply use the Landau-Lifshitz-Gilbert equation, which states that the dynamics of a spin will depend on the effective field that is applied on the spin, but will also depend on a term that breaks time reversal symmetry since it's dissipative. And this term depends on a dimensionless parameter that is called Gilbert damping. Now, if you take this equation, really the simplest equation to describe some ferromagnetic macrospin type of dynamics, and you linearize this equation with respect to the equilibrium position of the spin and invoke an Einstein-Primakov transformation, you will find that this term here, the one proportional to the Gilbert damping, gives rise to a non-Hermitian contribution to the Hamiltonian. So this was something supposedly known already since a long time, but it wasn't really discussed because we didn't know how to really treat this term. It's been only recently that there has been a really intense interest in the community concerning developing topological theories for non-Hermitian systems. So this field started growing and growing, I would say, in the last 3 and 4 years. And one of the most interesting things is that at the beginning, this seemed to be a sort of regularization problem. How do we fix things if there is some small non-Hermitian term? But actually analyzing the topology of these non-Hermitian systems, people found that this type of system can support really unique phases that have no Hermitian counterparts. So they are far more interesting than just being a trivial generalization of Hermitian systems. There have been many phases and many interesting phenomena that are currently debated and under active consideration. Here I will discuss 2 of them. In these systems, first of all, people realize that there can be topologically protected edge states, even if there is a non-Hermitian contribution to the Hamiltonian, and certain systems with special symmetries will support a bulk that is equivalent to the Hermitian bulk, so a bulk that has a purely real energy. But there will be edge states that are topologically protected that come in complex conjugate pair. So you can find edge states that have an imaginary energy which is positive or negative, and therefore are lasing in the language of photonics or lossy. So there have been already many proposals on how this type of edge states, especially the lasing one, could be deployed. On the other side of the spectrum, where nothing really resembles Hermitian systems, we have some non-Hermitian systems in which the bulk edge correspondence is broken. So let me just remind you, bulk edge correspondence is this idea that we have a correspondence between a periodic boundary condition and open boundary condition spectrum. So we can deploy the periodic boundary condition spectrum to define some topological invariant, and then we can look at the open boundary condition spectrum and see that this topological invariant corresponds to some edge states in our system. And this principle relies on Bloch theorem. So the striking realization was that in some non-Hermitian systems, Bloch theorem does not hold. We cannot describe the bulk wave functions as delocalized Bloch functions in our system. Instead, a different opposite type of phenomenon emerges, which is called the skin effect. And the skin effect is the localization of a macroscopic number of bulk states, bulk wave functions at the boundary of the system. And both these effects have been understood and realized in one-dimensional systems, and they've been also probed from an experimental perspective. They've been not only probed, but I would say engineered in metamaterials and photonic systems. So you can engineer these lasing edge states by having a system with a unit cell that contains 2 sites, and judiciously tuning the gain and loss between these 2 sites. On the other side, the skin effect can be easily understood only in 1 dimension in the context of a model in which there is an asymmetric coupling. So this asymmetric coupling is breaking the hermeticity of the model, and it's telling you that it's more convenient for a wave function to go right instead of left, or vice versa. And in these terms, it's kind of easy to see why a bulk wave function will accumulate on one side or another. But when it comes to generalizations of these systems to higher dimensions, I would say that the investigation is still relatively unexplored. And what is also important is that it seems that a naturally occurring solid-state platform to study this effect is still lacking. As I told you, these effects were measured, but in systems that were very judiciously engineered. So let me try to make the case that maybe magnetic systems might represent a platform, a solid-state platform, to look at this type of physics. So what are the key ingredients that we need? Definitely one key ingredient that we need is loss, but that's definitely not a problem for magnetic systems. Actually, we would like to get rid of these dissipations in many occasions, and we just cannot. On the other side, we also would like to be able to control loss and ultimately the effective lifetime of quasi-particles, and we can do that by controlling the gain. It turns out that we have already very well-established experimental techniques that allows us to control the gain, and I will show an example today. For example, one of them is spin injection, but also AC fields, for example, can do the job. So generally, I believe that the application of these non-emission topological theories to magnetic systems has a twofold advantage. So on one side, applying this type of theories to emission system can maybe finally shed light on the topologically protected magnon edge states that people had been searching for, and maybe we could not fully detect and control because dissipation was not yet accounted for. But on the other side, magnetic system might also serve as a platform to test unconventional non-emission phenomena in higher dimension. So I will discuss both these 2 sides of the problem. I will first describe our proposal of a non-emission magnetic topological phase, and how we believe that it's possible to engineer lasing edge modes in an array of spin-torque oscillators. And then I will talk about the emergence of a skin effect in a spin orbit coupled van der Waals ferromagnet. So let me start with our first proposal. When we started learning about non-emission systems, we decided to look at some spin torque building block as really a starting point for realizing a similar non-emission topological phase in a magnetic system. So a spin torque oscillator is nothing but a tri-layer composed of a fixed layer, a spacer, and a free layer. And for our purposes, the only thing that we need to know about this system is that a current will pass through a fixed layer, fixed because the magnetization direction is fixed. It will get spin polarized, then go through the spacer and exert a spin torque on this magnetization, this magnetic order parameter. So what we are really interested in is only the dynamics of this magnetic order parameter and the fact that we can tune it by spin current injection. So let's look at the dynamics of this isolated spin torque oscillator. Again, here we are just looking purely at the long wavelength LLG type of dynamics. So we will have some effective field that leads to a FMR frequency. We have a damping term, and now we need also to include the action of a spin torque. So we can work in the linear regime, which is a very common assumption generally in this type of problems. So we assume that mostly the magnetization is aligned along the z direction, and we look at small fluctuations with respect to the equilibrium position. The small fluctuations can be described in second quantization language as magnons, and ultimately by invoking the Heisenberg equation of motion, we can find the Hamiltonian. This Hamiltonian, it's the Hamiltonian, the linearized version of this type of dynamics. And here we find the usual Hermitian term, which tells us what is the FMR frequency of these modes. And here we find the non-Hermitian terms, in which it becomes obvious that the spin current, if polarized in the proper direction, acts against the damping. So from a physical point of view, I think it's quite simple to imagine our order parameter is damped, and then we pump spin current in, so we pump extra spin angular momentum, therefore more magnons in the system, and this will counteract the magnetic dissipation. So that's how this term is acting. Now we decided to couple them. As theorists, we couple them in a very imaginative way. So probably this is going to be a bit tougher to do, obviously from the experimental side. But we imagine that there are magnetic spacers, or maybe a common magnetic spacers, connecting different spin torque oscillators. And I'm labeling 1A and 1B because I want to create a unit cell that contains two of them. Why? Because I want to modulate the RKKY-like coupling between two different spin torque oscillator. So here we have this exchange-like coupling with a certain strength, but this one will have a different strength. And probably some of you can recognize in this a sort of SSH model. In our case, a non-Hermitian SSH model, in which we create this artificial system with two sublattices for unit cell. Our sublattices are the spin torque oscillators, and this J and J tilde are RKKY-like interaction mediated by some metallic spacer. Then we just need to do we need to control the spin injection, and this is the last thing that we need to do to achieve the system that we are trying to realize. So we decide to pump a spin current in the sites that we call A. So imagine that we have this array of spin torque oscillator. At each odd site, we are pumping spin current, while instead at the B sites, we don't pump any spin current. Maybe because there is not a direct contact here, or because we insert some insulator between this spin torque oscillator and the whole structure. The current that we pump, and this is pretty important in the A sites, must be properly tuned in such a way that at the 8 sites, the spin current overcomes the damping, and the loss and the gain at the A and B sites are equal in absolute magnitude, and of course, opposite in signs. So now we have this system. The first question that we asked ourselves is, well, we want to realize some topologically protected magnonic edge states, but how How do we know if an edge state is protected or not? Usually the easiest way to go about it is to find some topological invariant that is going to tell us that. And this principle is really the bulk edge correspondence principle. But we know that this is not guaranteed necessarily anymore in non-Hermitian systems. Sometimes a skin effect can appear, and I will talk about this later, and there can be a discrepancy between the open and periodic boundary condition spectra. However, we are working in a very special case in which we have both a symmetry called parity time symmetry and a region in which there is a real bulk spectrum. In this case, one can show, and Kawabata and the other authors have shown formally, that the bulk edge correspondence holds. Okay, so knowing that we can associate some topological invariants to the edge states, we can start trying to see if the edge states are actually there. So we diagonalized a system with 40 sites by exact diagonalization, and it's an open boundary problem, so there is no dependence anymore on the wave vector. I'm plotting the spectrum as a function of J over J tilde, and you can immediately notice that usually in a Hermitian system, you would just look at the real energy. Now we have both real energy and imaginary energy. There are three different phases of the spectrum. Let me focus on the one that for us is the most important and discuss the other ones later. And let's call this phase. This phase is called the PT unbroken phase. So here, the bulk is fully gapped. It's not only fully gapped, these are all the bulk modes, but is also purely real. So it does not have an imaginary energy. But you can see these lines, and these lines are edge states in the system. These edge states live in the bulk, live in the band gap, and they have a finite component of imaginary energy. So as I mentioned at the beginning, these two edge states, due to the special symmetries of the system, meaning PT symmetry in this case, come as a complex conjugate pair. So one edge state is Lasian and one here is lossy. Now, you might ask, what does it mean? I'm just looking at some linearized dynamics and I find these magnum modes that are Lasian or lossy. So how does this reflect in the classical spin dynamics? It does actually reflect, and that's pretty interesting. I will show you this in a second. Let me just show you what happens here. Here we enter in a so-called PT broken phase in which the edge states are still there, but they start becoming degenerate with the bulk states, and also the bulk states start acquiring a finite component of the imaginary energy. So the system, as I will show you, becomes more unstable. Now, can we associate a topological invariant? So this topological invariant was found not so long ago. It's called the global Berry phase. It's very similar to the Berry phase that we all know about it, except that now this is a property of two bands, not just of a single band. And phi and psi are the right and left eigenvectors of the Hamiltonian. So generally, if an Hamiltonian is Hermitian, if you diagonalize H or H dagger, you will find the same set of eigenvectors, since the Hamiltonian it's equal to this Hermitian conjugate. But when you have a non-Hermitian system, this does not happen, and you need to define these two different sets of eigenvectors. Anyway, we can calculate this global Berry phase, and it's an integer equal to the number of pairs of gapless real energy edge modes. So here in this region, the PT broken region, the global Berry phase is equal to 1. This means that we have edge states and they are topologically protected according to this invariant. So we can generally divide our phase diagram in three different sets. We don't really care about this side because here we don't have topologically protected edge modes. But here we have topologically protected edge modes. They are protected also in this shaded area. However, here they become degenerate with the bulk modes. So let's us focus first on what's happening in this part of the diagram. Yes, so now let's try to go behind the linear regime. Up to now, we have just looked at the linearized dynamics, so a Hamiltonian description of our system. But what we can do with magnetic system, and we cannot do in many other non-emission systems, is to have a direct correspondence between linear and nonlinear dynamics, because we literally linearize the LLG equation of motion, which we know. So magnetic system gives us also this opportunity of looking at nonlinear effects. So what would you expect classically? Classically, you have an array of spin torque oscillators, and you are pumping spin current that exceeds the damping in this one, and in all the other odd sites that I haven't drawn. So what you would naturally expect is that all these spin torque oscillators in which you're pumping spin current will start precessing almost immediately. And then after some time, due to nonlinear effects and coupling, maybe also the B sides will start precessing. So that would be, I would say, classically a very reasonable expectation. Let me show you what we actually observed. We simulated the nonlinear LLG equation. I'm plotting, I'm parameterizing the magnetization by some precession angle and by the experimental micropower that the magnetization precession can emit. So here we are running simulation for the PT unbroken phase. Let me just remind you, we have a purely real bulk spectrum and one lazy edge state, one lazy magnon edge state. So this was in the linearized picture. What happens in the nonlinear picture? Well, what happens in the linear picture is pretty surprising. We start pumping spin currents in all these sites, but the only site that starts precessing is the spin at the edge. And this is a topologically protective microwave emission. We tried to run this simulation for a long time, and in many realizations, the bulk keeps staying inactive. So this is definitely an effect that you would have never expected just from a simple classical perspective. Is this related to the phase, to the topological phase? Well, it seems to be definitely related, because when we move far away from there, so for example, we start moving here we can see in our simulation that the lasing edge state, the spin that corresponds to that growing magnon population, start precessing first. But then after a while, all the other spins will also start precessing, and these are really the spins associated with the bulk modes that become degenerate with the edge states. So the signal that we expect is very different. And I don't think I reported here, but if you start really moving further into this region, you would just see that all the bulk edge states start precessing exactly as you would expect from a classical standpoint. We are working currently on understanding the robustness against perturbation. So the question that underlines this research is, well, is this experimentally realizable or not? So we're looking at the thermal dynamics and the effect of perturbation. Of course, temperature does not help. More you heat the system up, more you would expect that also the bulk modes start hindering the signal of the edge states. But there is definitely a temperature regime in which all the prediction that I just show you just hold. We looked also at the possibility of some dissipative couplings mediated by these metallic spacers and at the effect of dipolar interactions. So the answer is that it all, of course, depends on the values of these perturbations and the temperature regime. But at low temperature and for small perturbation, the behavior that I just described to you still holds. So hopefully this is something that maybe could be experimentally realized. So let me sum this part before I move to the next one. We looked at the linearized dynamics of this couple spin torque oscillators, and we saw that if we judiciously tune gain and loss, we can realize a non-emission SSH model. We saw that this a non-emission SSH model can support some lasing edge state, and this lasing edge state, this magnon with the positive imaginary energy, really reflects, really has an effect on in the classical nonlinear spin dynamics. We looked at experimentally relevant perturbation. I think in general, some topologically protected microwave emission in this type of spin system can definitely find many applications. But what I think it's maybe more interesting is that in this case, including magnetic dissipation rather than trying to neglect it, led us to observe a new phenomenon such as this lasing edge states, which we would have never found as long as we neglect dissipation. So with this, I'm concluding this part and moving forward to the other example that I mentioned at the beginning. So here we're moving really far away from every type of properties that has a counterpart in Hermitian systems. As I mentioned at the beginning, for decades, the application of topology to condensed matter relied on the principle of a bulk edge correspondence, and also on the idea that we can use block theory to describe our states. Turns out that these principles, from my understanding, always hold for Hermitian systems, but I'm happy to be proved wrong, but they do not hold necessarily for non-Hermitian systems. And one of the consequences is that the bulk states cease to be block states, become non-block states, and start accumulating macroscopically at some boundary of the system. This was definitely well understood and realized in one dimension in this very simple model. That I would say it's even trivial when you tune the coupling in such a way that a wave function will travel more likely to the right than the left, but it's not yet fully understood in higher dimension, and has not, again, to my knowledge, been observed in naturally occurring solid-state systems that are not finely engineered metamaterials. So let me show you our model. We started looking for this effect, or we tried to understand more about this effect and its manifestation in magnetic system by considering a van der Waals material. So, and there is no specific reason why we did that. We were working with the systems in different contexts, and we just started looking at this system. And here, let me show you the Hamiltonian. We have some exchange, both nearest and next to nearest neighbor, a magnetic field, and we have DMI, which is allowed by symmetries in symmetry in many van der Waals magnets, such as chromium trihalide. So this is the Hermitian part of the Hamiltonian. Now our question was, well, in general, if you want to see a skin effect, we need to capture dissipation within a lattice model. So how can we describe magnetic dissipation in a lattice model, and hopefully in a way that is valid over all the first Brillouin zone? So it turned out to be a quite challenging question. First of all, there are many sources of dissipation, and this is all very material dependent, but you will have to take into account magnon, phonon, magnon impurity scattering, magnon electron scattering if you're moving away from the insulating limit. So a microscopic comprehensive description of these interactions is very challenging, and I could not we couldn't really find it everywhere, so we believe it to be a yet untackled task. Also, usually dissipation, as I was describing just a minute ago, is treated in magnetic system in the long wavelength limit. So we use LLG phenomenology or some perturbation theory, but it's not necessarily incorporated in lattice models that are valid over the first brilliant zone. So we started moving away from previous theoretical works and try to see if in ab initio or experimental works there was something that was more fitting our needs. Turned out that there is, but there is a caveat. For example, there are some ab initio calculations that provide a continuum expressions for the broadening over the first brilliant zone, but indeed these expressions are continuum, so they cannot be readily incorporated in the lattice model because they do not respect to start with the transitional symmetry of a lattice model, and in this case, for example, the C3 symmetry of this model. So what we decided to try out is a phenomenological approach that respects the lattice symmetries, and then we try to fit our phenomenological ansatz to some ab initio or experimental results. So in this case, since we are considering an honeycomb system, we started going through the literature, and we saw that there was one work, an ab initio work, in which they looked at magnon-phonon driven dissipation. So they could calculate the band broadenings, the associated relaxation time of magnons in this ab initio simulation over the full brilliant zone of the hexagonal lattice. In an honeycomb lattice, you will have two sublattices, therefore ultimately two eigenmodes, some acoustic mode that is an in-phase mode and some optical mode at higher energy, which is out of phase. Here, this broadening turned out to scale as k square, and this one from their simulation, it's a constant. So this cannot be readily incorporated in our lattice model. It does not respect our translational and C3 symmetry. So we make these ansatz for the broadening. And for the broadening, very important point of the eigenmodes. We make these ansatz, and here our K's are fitting parameters to their results. So we make such ansatz, and then we fit the ansatz to their result, and we have three fitting parameters, so it's a pretty good fitting. Now the question is, what are these terms? So we took these terms from the eigenvectors representation, and to try to make more sense of them physically, we did change our basis and go back to the sublattice real space base. So this is the Miltonian in that form. There are many terms. I would say that maybe better to focus on this part than all the details of the multiplicative coefficients. In few words, we find some terms that they just express local dissipation. So this is a simple Gilbert damping-like term. Now, it was found that the acoustic mode has a broadening, a relaxation time that is k-dependent, which signifies that there is a non-local dissipation acting in the system. So these are the terms that we find. And for some of you that are maybe familiar with the phenomenology of spin pumping, these terms are really reminiscent of non-local spin pumping terms, that are due to electron-magnon interaction in this case. So here you have J, and you know that you have also a dissipative contribution due, in this case, to the phasing between magnon and electron spin. In our case, these are coming out from trying to fit the ab initio results of dissipation due to magnon phonons. So again, to our knowledge, there is not really a microscopic theory that is available, but it would be definitely very interesting to look into it. And then we have also some higher order, nearest neighbor purely dissipative terms that microscopically make less sense to us, because we tend to think that if we have a dissipative interaction, we will have also its non-dissipative counterpart. However, retaining or not this higher order terms does not affect our results. So let me show you our results. We took our Hamiltonian and we diagonalized it over fully open boundary condition. So here we have zigzag termination on one side and armchairs in the other. And one way to start looking at the skin effect, that's what has been done in literature according to its definition, is to look at the spatial distribution of the density of the right eigenstates of the system. So when we are at low temperature, here I think it's around 2 Kelvin, what we see is that all the bulk bands are delocalized throughout the sample. This is what we will expect from a block band type of description. So there is no skin effect, and this also confirms our usual assumption that in a long wavelength limit, things are quite well described by non-exotic effects. But if we start increasing the temperature, so here we are reaching this point, we observe the emergence of the skin effect. So the wave functions start localizing macroscopically at some edges of the sample. They are not distributed anymore inside the system. So what's going on? We try to understand, at least in part, what we see. So first of all, let's try to understand the temperature dependence. Okay, as you can see here, this is a plot in which I'm showing you in blue the acoustic, and here in orange the optical periodic boundary condition spectrum. So the one that you would obtain just by setting periodic boundary condition. The gray ones are instead the open boundary condition spectrum. You're of course observing a discrepancy between the open and periodic boundary condition spectrum, but this is also another expression of the emergence of the skin effect and the breakdown of the bulk edge correspondence. So here, we can see that the wave functions are delocalized, and we are looking at states up to this energy. Here, our spectrum for the acoustic mode, it's a line. Here, instead, it becomes an area. So in general, in correspondence of an arc or of a line, the mapping between from momentum to energy is 2D. 2D from momentum to energy 1D. So for a general wave impinging at the boundaries, you will have infinite reflection channels, and you can describe an open boundary eigenstate as a superposition of block waves. And here you have your block waves. But when you have a finite effective spectral area, the mapping is 2D on 2D. So the reflection channels are much more restrictive, and your state cannot just be described as a superposition of block waves. So this concept matches our results, and it was already proposed in this paper. We found actually that this area law that we looked at, this area law that was proposed in this paper has to be modified accordingly. But for the interest of time, let me skip this part. So to end, what are the key ingredients of this effect? So first of all, we need a K-dependent dissipation, some non-local damping that survives the real lattice representation. So that even when Fourier transform is still there in the real lattice Hamiltonian. So why it needs to be K-dependent? Because if it's just a K-independent term, like the usual Gilbert damping in the LLG phenomenology, it will just be a line. So there is no area, and the skin effect is not going to emerge. So we need this non-local type of dissipation. But is this enough? If we switch off DMI, we find that no matter if there is non-local dissipation in the system, our finite spectral area vanishes and the skin effect disappears. From a mathematical standpoint, you can realize that by noticing that in the absence of DMI, the imaginary part of the energy becomes a function of the real part of the energy, and therefore it must be a line in the complex energy spectrum. But more physically, we can try to look at this property as, to observe the skin effect, we need some interference, an interference between an interaction that is by definition non-reciprocal, such as the Dialoghinsky-Mourier interaction, and some non-local magnetic dissipations. So it's really the interference, at least in our model, between the two that is playing a very key role in accumulating the bulk states at the boundaries. So let me conclude with this. So here in general, we try to develop a phenomenological treatment of magnetic dissipation in a lattice model. It would be really interesting to try to develop microscopic theories that can reproduce a similar model. And we find, surprisingly, the emergence of the skin effect in a magnetic system. In our case, is due to the interference between non-local dissipation and non-reciprocal interactions. We can understand it via this effective spectral area law that we proposed, but I think this is a really first step. There are still many things to understand. What is, for example, an ideal platform in which we can realize this system, and especially what are the experimental observables? So this is a really non-trivial question, because you can look at this accumulation and think that this is a simple Magnon density of state. But you're working with some bioorthogonal system that is can be just described in real space representation. And the green functions operator do change a lot with respect to the conventional one. So that's also something to really look at. And I just ultimately want to thank Rembert and Hilary, with whom I did the first two works that I discussed, and Kyung-In Dang is my postdoc, and we work together on finding this skin effect. And thank you for the attention.
Thank you. Thank you very much, Benedetta, for a very nice presentation. So I think now we are open for questions. And I'll promote you to panelists as well, to everybody that asks questions, so that way you can ask them directly. So let's see, Sumit, I think hopefully you will come online in a second. You're promoted, or yeah. Okay. In the minute, I'm going to ask a question that is already written in there. Let me see. I think, okay, Sumit, go ahead and ask your question.
Yeah. Can you hear me now?
Yeah, we can hear you now.
Okay, great.
Yeah.
Thank you for the nice talk. What I want to ask is the density of state you show for this skin effect. Do they have a finite lifetime, or they stay like that forever?
No, they do. They are associated with the finite lifetime as well. Okay. I also want to stress that this is not exactly a density of state as we think about it in an Hermitian system.
So their lifetime, is it associated with some other system parameter, like any other time scale of the system itself?
Yeah, absolutely. So it's associated. So in general, when you would write down, let me show you. In our approach, we have an Hermitian part of the Hamiltonian, and then we write down an ansatz for the broadening, which you can think as the inverse of the lifetime. So it's associated with this with these parameters that we plugged in.
Okay, so this broadening itself is time independent.
Yeah, the broadening is time independent. Yeah, yeah, the broadening is time independent. Yeah.
Thank you. That's all.
Thanks. Igor, can you go ahead and ask the question? Can I unmute yourself? Yeah,
thank you. Question is the following. When you show the spectral area, then there is a very big difference between behavior of system at high frequency and low frequency. What is the physical reason?
Oh, yes. So let me just clarify with you. You're talking about this spectral area versus the blue one, or you're talking about this with respect to this?
I'm talking about this right-hand side square.
Yeah. Okay. So
Localization you
yes.
observe namely in higher frequency, first of all, and then there is asymmetry between X and Y.
Right. Yes. Okay. So let's say these are, our straight from a numerical exact diagonalization results. But our ways to understand this, it was also proposed in a slightly different form by Chen Feng and some other co-authors. So the idea is that here, when I plot this one, I'm looking at all the states up to this energy. So all the wave function up to this energy are contributing to this plot. Here, the spectral area is actually a line. So we have a mapping between from momentum to energy. This is a 2D system that is 2D to 1D. So in theory, you can have really infinite reflection channels. There is not a strong constraint in this mapping. And you would expect that your states can be expanded as a superposition of block waves. So that's the way we look at it. Now you're going here. There is this other green line. This green line corresponds to the energy at which we plot this this one. Here it becomes an area. So it starts becoming a 2D on 2D. And your solutions cannot be any longer block waves. So they start, which you would expect to be just delocalized in a symmetrical way throughout the system. They start localizing. The question about the asymmetry, it's an interesting question. So we have some and wavy argument about how the non-reciprocity of the DMI combined with this non-local damping makes things accumulate at the armchair rather than the zigzag termination. But I have to say it's very end wavy. Yeah.
Okay, and one more question about okay, maybe later. I formulate more exact later.
Okay. Another question was Marius Michael, which is not around anymore. It was if they are called box states, if they accumulate the boundary, why was the different? No, so it's just like bulk states that merge into the boundary, or why the nomenclature?
Oh, so okay, I'm thinking. So I'm talking about bulk states. If you have a system and we have periodic boundary condition.
Well, you call them bulk states. You call them bulk states that become that accumulate in the boundary. So why are they called bulk states if they accumulate in the boundary?
That's how they are right. That's a good question. That's how somehow in literature
that's how people
have been defined. So the idea is that you have an open boundary condition system. You can you use this Hermitian terminology, and then you say, well, they are not anymore in the bulk as we would expect.
So then maybe since, I'll let people ask more questions if they want. Wait for the answer raise. Go ahead.
If you don't mind,
go ahead, Igor.
I will ask about two things. One is generation of spin waves. Does it mean that actually system wants to form bound states of many spin waves? You understand what I mean? That in linear theory, you have some laser, as you call it, effect, but actually it may mean that many spin waves are going to form bound states.
Yeah.
They are known. that actually exact solutions show that there appear some bound states, and even many bound states appear. So wave function contains many waves which are bounded. So this is one question about this Lezing effect. And another question about the definition of topological states, how do you calculate it if you don't have actually K, which is conserving, and block states you don't have. So in that respect, you don't have some line along which you have to calculate maybe eigenstates of this system you have to use instead of K.
Okay. Yeah.
You've shown some definition of topological state. Right. There is integral over K.
Right. Okay.
Yes.
So that.
What is K? What is quantum number?
Yeah. Okay. Let me answer first to this question. Yeah. So I think the definition that I think two things are relevant to this. The definition that you're referring to is probably this one, right?
Yes.
Okay. This so one thing to be said about this system, PT symmetry is a PT symmetry combined with this purely real spectrum. It's a system in which instead the bulk edge correspondence perfectly holds, an open boundary condition and periodic boundary condition give you the same results in terms of gaps and so on. So ERK is absolutely, I would say, well defined. That said, you might indeed ask, what happens when the bulk edge correspondence is broken? How can I calculate some topological invariant instead?
Yes.
So, yeah, that's not an easy question, but it was answered. Usually these questions, they have been answered, system by system. You notice that in our case, we have DMI. And actually, if you look here at this, you see, if you look at the periodic boundary spectrum, there is a gap, right? Because we have DMI. We calculated the open boundary spectrum. They didn't put a lot of emphasis in this, but we find edge modes. How do you calculate the Chern number of these edge modes? They are, if you want, I could send you. There have been recent report in literature in which they develop a scheme. Suddenly, K is called some generalized Brillouin zone scheme in which K is no more a real number, but it becomes complex. And by doing so and putting appropriate constraint, you can reproduce in periodic boundary condition what you observe in terms of edge states with open boundary condition, even when the bulk edge correspondence is broken. So that they have been
where is guarantee that this number remains integer number? So the charge is conserved indeed, even when you have these states which are containing imaginary part.
Yes, there are proofs in terms of Z, topological invariant. They're somewhat convoluted, but I'll be happy to send it to you. I don't think that there is a very general proof of this for any type of topological invariant. It's more addressed case by case, but they turn out to be, they're constrained to be integers.
Okay, first question was about formation of bound states. In your numerics, you should observe it, I believe.
Right. So I would ask you more maybe clarification about your definition of bound state. So do you mean that the wave functions that we observe there, the one that are localized, will be a mixture of different states, of different spin wave states?
Well, I would say that it will be not simply mixture, but probably Well, bound states, which means that you cannot consider any of these waves separately. You have to describe them as by 2 Magnon function, 3 Magnon function, and so on. Which cannot be represented in the form of product.
Yeah, we did not. No, that's interesting. We did not look at that in our solution.
Okay, maybe you have this opportunity since you have solution. Very interesting. It would be observed. Okay.
Yeah, no, definitely. Yeah, maybe.
Yeah, something.
Thank you.
So let me ask Alexander, go ahead and ask your question, and then I think I will wrap it up. Go ahead.
Hey, Benedetta, nice talk. This is Alexander Moog from the University of Basel. I would like to ask 2 questions about the Magnon-Phonon interactions that you used for your van der Waals calculations. Yeah. One question would be the type of Magnon-Phonon interaction that is considered there. Is it a kind of 4-particle interaction that conserves the number of magnons and phonons in the sense that you would need finite temperatures to install these interactions? Or is it more like a 3-particle interaction that a magnon could spontaneously decay into a magnon and a phonon or 2 phonons?
Right. So that's a really interesting question, and I think it would be interesting to start thinking about it, because we have our approach is phenomenological in the sense that we really do not have any microscopic behind this. We started with the idea of let's go and do this microscopic, and let's try to do this and get like some expression that we can deal with, not in the long wave limit, not in the continuum limit, but in a proper lattice model, and that's really a problem per se. So these interactions, the data that we are fitting this interaction to, so both the K dependence and the magnitude, these are ab initio calculation in which there is no, let's say, explicit quantum mechanics. They are just thinking about 2 spins that are connected, and these phonon are making the position of magnons vibrate in a random way. They take place at finite temperature, but I cannot, I think it would be really interesting to look at this type of terms that we obtain phenomenologically and reproduce the ab initio calculation and try to understand if, do we need this 2 magnon, 1 phonon, or 2 phonon, 1 magnon, or 4-particle type of interaction? Then we can integrate out the phonons and obtain something like this. I don't know. It's kind of a open question.
I see. I guess my second question is kind of related to that. It's maybe a stupid question, but I was just thinking.
Oh, no, don't worry.
So a non-Hermitian Hamiltonian is always something like an effective theory, because you're kind of neglecting the bath into which you would dissipate energy. I was wondering if you now write down the Hamiltonian with magnon and phonons included, then of course this Hamiltonian that takes care of both the magnetic and the structural lattice would be Hermitian. So my question is, this interesting non-Hermitian physics, would it disappear if I just increase my system and take the bath into account? Or how do I have to think about that?
So definitely, if you think that in the system, the only quasi-particles that you have are magnon and phonons, it's a closed system, so you're completely right in the sense that the full Hamiltonian of the system should be Hermitian. Would that it's a good question. Would that disappear? So from an intuitive point of view, for me, what really matters is what you measure, right? So you know very well that if you're measuring spin quantities, you're looking at the ferromagnetic resonance or at the spin transport experiment. You do measure this dissipation. So I don't know what will happen if you add the phonons in the system, but I think that there will be still an effect associated with the accumulation of spin states at the boundary. As much as when you probe an actual system, you know that phonons are there, but you can see clearly the effects due to its dissipation in spin properties.
Okay, thank you very much.
Okay, great, thank you. It's okay with that. I think we. Oh, Helen, if you have a question, go ahead and ask the question.
Yeah, I wanted to also ask a question related with the previous. With this dissipation, the effective dissipation depends not only on the Gilbert damping, but on the this spin pumping. So it's dissipation like a channel, which can be positive or negative. Yeah. So if current is zero, the effects will disappear, or they will still proceed. So do you need this external pumping of energy into the system in order to have these edge states?
So actually, let me try to let me try to reformulate this. It's again a good question, but I think this is also a question that requires an understanding of the microscopic model, which is something that we yet just obtain phenomenologically. There have been this simulation that account for temperature, magnon-phonon interaction, and so on, that tells us that there is a thermal equilibrium in the system, a dissipation that depends, that is non-local, so as some K dependence. And that leads us to this Hamiltonian. Now, this Hamiltonian is reproducing some data of a system at thermal equilibrium, so I would expect the process to be there. But since I do not really understand yet the microscopic nature of the process, and when I say spin pumping, I'm just making a parallel with the similar terms. But here there are no electrons. There is no electron magnon, no current. There is not really current, so I'm not, sure. Since I don't know the microscopic, I'm not sure what is the essential ingredient here from a microscopic point of view.
But what confuses me, maybe I do not understand the details, but if I think generally from thermodynamic point of view, I forget about microscopics. There is a second law of thermodynamics, which says that if I have only internal dissipation, then it stands alone from the Hamiltonian. So the energy cannot be transferred from one part to the other. It goes somewhere outside of the system.
Right.
But if the system is open, then I can understand this. So then I have an energy from outside, and this energy can be distributed in different ways. So this was my question on the more general.
Yeah. No, sorry. Then I misunderstood your question. This Hamiltonian is telling us something about an open system, like there is an open system of magnons that have a finite lifetime. Spin pumping was probably a misleading term. Here there is just a finite lifetime that is expression of dissipation. Where does this energy go? Where do the magnon go? For example, in the phonon bath. Yes, that's the way I would think about this.
Thank you.
Okay. I think with that, I think we're to the end of it. Lots of nice questions and interactions. So very fascinating new physics on this non-Hermitian systems and driving systems. I'll have to look into some of the things that I'm interested in afterwards and might come up with some follow-up questions for you. So thank you once again to everybody. I think at this stage I will stop the live streaming.